So thank you for joining us for today's ATA educational webinar, Getting Started with Simcenter Nastran Multistep Nonlinear Solutions. I'm your host, Scott Tebow from ATA Engineering, and your technical speaker today is Miles Hayden from our Virginia office, Herndon, Virginia office. Before we launch into the presentation itself, I just want to give a quick introduction to our sponsor, ATA Engineering. So who is ATA Engineering? ATA Engineering is an employee-owned small business with a full-time staff of over 190, probably 200 by now, the majority of whom are degreed engineers. We have a heavy preponderance of master's degrees and PhDs among our staff who have been recognized as subject matter experts by respected professional societies like the Society of Experimental Mechanics, ASME, AIAA, and many others. ATA provides high-value engineering services to help solve your toughest product design challenges. We work principally in the fields of aerospace, spacecraft, hypersonics and composites, defense, industrial and mining equipment, and we have a very interesting practice in themed entertainment. Think roller coasters, animatronic figures, and that sort of thing. We serve our customers worldwide from our offices across the United States. Our headquarters office is in San Diego, California, but we have branch offices located in Los Angeles, in the Bay Area, in Denver, Albuquerque, Huntsville, Alabama, and Herndon, Virginia. Our principal services are in the area of design, analysis, and test, but we are also a Siemens Platinum level solution partner. So we provide software licensing and technical support and services for a full range of Siemens engineering and design software. This includes NX, Nastran, the topic of today's webinar, Femap, Star CCM+, Simcenter 1D, Simcenter 3D, Teamcenter, HEEDS, and a host of others. We offer hotline support available from 8 a.m. to 8 p.m. Eastern Time. And we also provide implementation services, integration services, and training. In fact, Siemens is the preferred training provider for Simcenter Nastran, and most of the Simcenter Nastran training materials used worldwide were developed under contract by ATA Engineering. And we are a certified expert partner with validated expertise for Femap, which includes Nastran, Star CCM+, and Simcenter 3D. For more information on the products from Siemens that we provide, you can visit our website at ata-e.com/software, and you'll be able to download brochures or catalogs or other information about the software that we sell and support from Siemens. Now I'd like to introduce our principal speaker for today, Miles Hayden from our Herndon, Virginia office. Miles is an expert in Simcenter 3D and Nastran and quite literally wrote the book on Simcenter 3D multi-step nonlinear analysis. So it is a privilege to have him here today to give us a brief introduction to this technology from Siemens, but you should know that there are full classes available on this, this product as well as other specialized topics around Nastran. Take it away, Miles.
Thanks, Scott. So I'm going to get us started here with the starting from the basics. With just first off, what does nonlinear analysis mean? When we are talking about nonlinear analysis, generally it's describing a number of different types of structural analysis, but the thing that they have in common is that the structure is no longer responding in a linear manner to your applied boundary conditions. So just for a couple of examples here, you can have just a simple, axial test specimen that you're loading and pulling through yielding, and you can see that as you load that structure, it is definitely deforming in a not linear manner. But that's not the only type of nonlinearity. You can also have large displacement or contact type nonlinearities that I'll talk about coming up. This little badge clip plate shell model shows that sort of thing as you deform it to open it up so it can clip onto something. So just since we want to talk about nonlinear, we need to compare them to linear solutions. So just as a reminder, linear analysis is based on linear elastic theory. So your materials are going to have a linear stress-strain relationships. Your displacements and your strains are assumed to be small. Your stiffness is not altered by any deflections, and your loads are independent of your deformation. The counter to that is nonlinear, is basically the opposite of all of those. So you can have complex stress-strain relationships. You can have large displacements or strains. You can have your displacement reduce or increase your stiffness, and your loads can depend on your deformation. Another major difference between linear and nonlinear solutions is that a nonlinear solution is iterative in nature, and it's going to converge to a state as it's iterating. So the plot on the right there kind of shows just a notional sort of path that your solver would follow perfectly if it was, a real world behavior of a simulation, and you're trying to converge up to a certain load state at the top there. So you're going to iterate that solution, and this particular example is showing 3 different iterations with 2 stiffness updates to get to that converged state where you're within some convergence tolerance of the final desired state. So there is obviously, since you are iterating and converging, there is work that the solver is going to be doing while it's running that is beyond the standard linear analysis. So nonlinear solutions can be significantly longer than a linear type solution where you're just solving the F equals kx type equation in a matrix form. So just talking about reasons that you might consider using a nonlinear solution, the first and one of the most obvious ones, and the one that we're going to do a demo later on, is that if your structure is loaded highly enough that you have exceeded the yield threshold of your material, then you're getting into the nonlinear material behavior of that model. So that dog bone is a perfect example of that. As I mentioned, contact is another perfect example of a nonlinearity where, because contact is creating a difference in the load behavior and compression versus tension, that is absolutely a not linear type of behavior. Additionally, if you have a model which is just going to be deforming significantly enough that your directions of your loads applied to it need to be updated, that is a situation where you're going to need a nonlinear solution. Additionally, with respect to deflection, if your structure is deforming significantly enough that the stiffness of the structure is going to change, and a drum head is a classic example of that, that is definitely a situation where you're going to need to consider nonlinear behavior. And then there's also other advanced material behaviors that are nonlinear in nature, be it hyperelasticity or any of those kind of things, where you would need to consider a nonlinear solution. When we do talk about nonlinear solutions, we generally break it down into 3 different categories of nonlinearities that are in the model. The first of which is geometric nonlinearity, sometimes called large displacement. In fact, the Nastran language calls it a large displacement solution, LG-DISP. So that geometric nonlinearity is basically describing the condition where the motion from your initial state is no longer negligible. So that would account for the situations where, for example, that drum head, whereas the drum head is deforming, it is stiffening and able to take the vertical load through tension of the membrane. A clothesline is another classic example of that. It also could be the situation where you need your loads to update directionality as your structure deforms and moves through space. The second category is contact, exactly what it sounds like. It's two or more bodies exerting compressive or frictional forces on each other when they're touching, but under tension, they separate and do not create force. So being that there's force in one direction and not in the other, that is inherently nonlinear. And then lastly, there's material nonlinearity, which is whatever form of material nonlinearity you're modeling, be it plasticity, hyperelasticity, creep, any of those nonlinear types of behaviors, and there's many others I didn't mention. But basically, your material is no longer proportionally responding to your load. So it's, basically invalidating Hooke's law, any of those types of material models. So those are the three categories of nonlinearities that we're going to talk about. And conveniently, when we're dealing with these inside the Simcenter 3D interface, it breaks these kind of things up into those categories accordingly. When we are talking about nonlinear solutions in Simcenter Nastran, we do need to talk about the capabilities across the different solvers, because there are a number of different solvers that exist in Simcenter Nastran that have nonlinear capability. First off, the standard solution 101 that many of you are probably used to. It is capable of linear contact, and it can do bolt preloads. So because contact is a nonlinearity, technically 101 can do nonlinear things, but it's a linearized form of contact, so it's kind of a simplified model. The original nonlinear solvers in Nastran are the 106, 129 solvers. Those are long supported solvers that have existed for a while, but they, being older solvers, they are a little bit more limited in their capability. So you can see that, yes, they do technically support contact, but it's only through gap elements. But they are capable of large displacements, and plasticity, for example, are the most common reasons why you might use those if you're just doing a simple model with a single nonlinearity. Then we get into the next two, which is the solutions 401 and 402, which are called the multi-step nonlinear solutions. You will note that the solver base for those is different. So solution 401 is written in the standard Nastran DMAP with a Fortran base solver language, whereas 402 is a wrapper for the Samcef solver language. So the input deck and the output files from it look just like Nastran, but in the background, it's doing conversions and then running the Samcef solver and then converting back for you. So collectively, those are both the multi-step nonlinear solutions. You can see that they are generally very capable solvers. The reason they're called multi-step is because of this subcase chaining bullet here, where you can now, as a user, you can choose whether you want individual subcases to follow on to previous subcases. If you were in 106, that was required. And if you were in the former Advanced Nonlinear 601, 701 solvers, you could not chain those subcases, and you had to do tricks with time functions to get things to follow one another all within that one subcase. But for those multi-step solutions and the ones we're going to be talking about in the demo today, generally very capable solvers between the two of them. Not everything is in both, so you can see that only solution 401, for example, has the nonlinear elasticity, whereas solution 402 is the only one that has hyperelasticity, and to a lesser extent, large strains. 401 can only do large strains on solid-only element types. That's 3D solids and 2D solids, at least at this time. But that kind of shows you, and they also have modal capabilities as well. Then there's the 601 and 701 solvers, which I'm not going to spend a lot of time talking about because those are actually depreciated. Technically, you can still run them if you have older versions, but in the newer versions of Nastran, the capability to run those does not exist anymore. So they have kind of been, if you're familiar with them, those have been replaced now with the solutions 401 and 402. So since we are talking about the kind of advanced multi-step nonlinear solutions, and there's two of them, and a question that is often asked is which one should you use? Because they both seem pretty capable, and how do you decide which to use? A lot of that comes down to what they were originally started to be built for. There are some that have slight more strengths than others. So 401, because it's a bit newer of a solver, but it was designed with co-simulation, multi-physics type problems in mind when they started it. It tends to be better for those types of solutions. Whereas 402, because it's based on the Samcef solver and it's been around for quite a while, it's a little bit better at some of the more complex interaction problems. When you have large strains or large rotations in your model, it handles those a bit better. But just if you have really complex material models or you're involving lots of different nonlinearities at the same time, that's a time when you might start using 402. So obviously, I didn't mention all of the analysis types there, and that's because generally speaking, for most nonlinear analysis that you might do, either solution 401 or solution 402 is an acceptable option. So if you're just doing plasticity or doing plasticity with large displacements, for example, those are absolutely capable solvers for both of those. Either 401 or 402 can do that. So basically, what I tend to find is that you'll become more comfortable using one of them, and you'll continue using that one until it's no longer capable for the thing that you want to do with it. And then you'll go and try the other one. And these days, I find myself jumping back and forth between them from problem to problem, depending on how one is behaving versus the other with respect to convergence or things like that. So now we kind of get into I have a linear solution and I want to do a nonlinear solution. How do I go about that? So this is kind of the intro to the demo that we'll do in a bit. But in terms of the Nastran language, it's actually pretty simple to convert a solution deck from a linear solution to a nonlinear solution. The first thing, obviously, you're going to change the solution statement from a 1 to a 4. This is showing a 401, for example, but the 402 is very similar. The next step is that you're going to add a subcase with a callout for the analysis type of that subcase. And that is not strictly necessary in terms of adding the subcase, because you can just do the analysis equals whatever statement for the global load set. But I recommend starting it with a subcase in case you want to add further subcases later. And then the other thing that you're also going to be adding is a call out to a T-step card, which you then have to add in the bulk data section later, because that is defining how the solution proceeds through time as it steps. So in this case, we're defining a 1 second subcase with 10 increments, and we're requesting output at all of those increments. In terms of that analysis equals statement, there are 3 primary types of nonlinear subcases that you'll be choosing from when you're setting that statement. So first and foremost is the analysis equals statics option, which is your nonlinear static solver. And that's basically solving the f equals kx type solution in the iterative nonlinear sense. The time that you're using in that nonlinear statics solution is simply a scale factor that gets applied to your loads that don't have a time scale on them. So if you are applying, a 10-pound force in a nonlinear static solution, it will by default ramp from 0 to 10 throughout the subcase in which it is applied. Next is the preload type subcase, and you can actually think of the preload type subcase as a subset of the static type subcase, because it basically is a static subcase, except it occurs over 0 time. And the reason it exists is because when you have a preload type subcase, any loads that you have applied in that preload type subcase are automatically propagated throughout future subcases without you having to carry those load statements through them. So it's literally preloading the structure, so there's no reason you would want those loads to go away. That's the intent of that subcase. But it does occur over 0 time. It still will scale the loads. There's a load factor that it does, and it will ramp loads throughout that preload type subcase. But it's just considered a 0 time subcase because it's not intended to be any part of your nominal load sequence if you're doing one of those. And then lastly, there is the dynamics type subcases, which that's your implicit dynamic solution if you're using that. So that's your full equation of motion where you have your displacements, velocities, and accelerations considered, and your time is a real world time factor. So you might use that if you're doing a drop test simulation, for example, where you have a thing that hits a hard surface and then bounces around, and you're looking at the response dynamically to that impact event. Additionally, 401 and 402 do have modal subcases available within them, where you can basically create a snapshot modes simulation of the current state of the model where that modal subcase exists, or even for 402, you can do a modal buckling type subcase and see a linearized tangent stiffness matrix buckling solution for the current nonlinear state. So it's basically a normal eigenvalue buckling type solution, but it's about the tangent stiffness at the current state of that nonlinear sequence that you have been proceeding through in your solution. So if you are adding the nonlinearities into your model, there are some global parameters that you need to be aware of and that you will be using if you are adding those nonlinearities. So there is param mat-nl, param lg-disp, and param lg-strn, or large strain. And those toggle on those behaviors if you want them in your model. So in the Simcenter 3D interface, you can see that there are checkboxes for those to determine whether they're active. And that just sets those parameters for you inside of the Nastran language. If you are doing a material nonlinearity, you also will then need to do some sort of definition for the behavior of that material. And there are 2 typical options. If you're doing plasticity, it's going to be either a MAT S1 card or an M-Plas card. They both are generally available or acceptable for basic plasticity, but M-Plas is a bit newer, so it has more options like doing gray cast iron models or like Hill anisotropy type things, whereas MAT S1 is more of your standard isotropic yield, von Mises yield criteria type laws that most people doing metal analysis are going to be dealing with. Also note that if you are doing material nonlinear analysis, even if you give it one of these MAT S1 or M-Plas cards, it will not use the data that you gave it. It won't use your stress strain table unless you turn on that param mat-nl. So I've definitely made that mistake myself in the past. So just be careful that just because you give it a stress strain curve doesn't mean it's going to use it, unlike some other solvers that that do just automatically use whatever you give it. And then lastly, when you are running solutions 401 and 402, because they're nonlinear solutions that converge, there are lots of control parameters which are available to you to be changed to control the solution behavior to get better convergence or to affect just the overall behavior of the solution. There's global nonlinear control parameters, which are applicable to solutions 401 and 402, and that's the nonlinear control G card. And then there's nonlinear control cards there's one for 401 and one for 402. And the 402 always has a 2 on the end. And those are different for 401 and 402 because they specifically are tied to the way those solvers execute. And if you remember, the 402 is based on a completely different solver base, so that's why you need separate cards for those. The same goes for your contact control parameters. There's a separate one for both 401 and 402, but there's a lot of parameters for controlling your contact behavior, so they each have their own thing. And then there's a region control parameters, which is common for 401 and 402. But each of those cards has, it's basically a collector for a bunch of different parameters where you're going to be setting a parameter, then a value, then another parameter, then a value. So it's kind of the collector for all of the tweaks that you might be doing to these nonlinear solutions. And there is a lot of documentation in the quick reference guide if you are interested in looking through all of those. To talk about some of the commonly used ones that I personally find myself using, I'm just going to go through some of the major ones, let's call it. These particular parameters are available on both the solution 401 and 402 versions of either the nonlinear control card or the contact control card. So the first one is the INI-PNE card, which is, or flag, I should call it. And that's the initial penetration behavior flag. And that basically allows you to remove interferences or gaps in contacts before you start your solution. Then there's also the fric mod, which is the thing that you use to change the friction model that you're using. Then there's your solution control options, which has the DT init, where you can manually set your initial time steps, so the solution doesn't need a ton of increments, but if you want it to start with a very small time, you can, which, if you remember, time is equivalent of load. So if you want it to start with a small load, you can set it to have a very small initial time, and that will start your solution off very gently with a small load, but then the solution can ramp up the amount of time that it takes per iteration, so you don't spend forever solving with lots and lots of increments. Then there's the plastic parameter, where you can enable or disable plasticity individually for a subcase, which I will often find myself disabling plasticity for bolt preload subcases, for example. Also, just a note for the behavior of rigid elements between solutions 401 and 402, because this sometimes can be a little tricky in terms of behavior. So kind of a pro tip is that 401 has an option in the case control area with, you might be familiar with the rigid command, where it can either be set to rigid or Lagrange for a solution 101, and you might use Lagrange if you want your rigids to expand with a CTE, for example. 401 expands that to allowing you to have a linear behavior, which is pure 101 type behavior. There's stiff, which forces an internal conversion of your rigid element to a stiff beam that it calculates the stiffness of based on the overall stiffness that it's seen in your model. Then there's the nonlin option, which is still the elimination method, but it does include and account for large rotations in your model. And then if it's the auto option, which is the default, the solver is either going to use the linear 101 type behavior if you don't have large displacements in your model, or it's going to use the stiff beam formulation if you do have large displacements in your model. And then the difference in 402 is that it always is converting your rigids to MPC type equations internally, that the Samcef solution formulation for those MPCs handles large displacements and large rotations well. For a couple of 401 specific parameters, there is the auto scale parameter, auto scale, depending on how you want to pronounce that. Basically, it is a scale factor on your auto calculated contact stiffness or compliance. And basically, if you give it a value greater than 1, you're going to be increasing your contact stiffness. If you give it a value less than 1, you're going to be decreasing your contact stiffness. That's a common one because I find myself using because the contact behavior sometimes tends to be too stiff, and softening it a little bit is a way to get convergence a little bit better. Then you can also choose the pen type, which is the formulation for the contact, whether it's a compliance or a stiffness formulation that you're using. In terms of the solution parameters in 401, EBSTAB I find myself using fairly frequently. It's basically matrix stabilization, where it kind of does a 1e to the minus 10 factor on the matrix. It's especially useful if you have a free body that's not connected by contact at the beginning of the solution. It kind of gives it almost like a small, lightweight grounded spring to hold the model from flying off 10 miles to the right in the very first second that it gets any load. Then there's a PL lim parameter, which allows you to limit the amount of plasticity that the solution will allow from one iteration to the next. So that's a way to kind of control the speed of the subcase when you have a lot of plasticity in your model. And then there's the EPS bolt parameter, which you can use to change the convergence criteria for the bolt preload convergence in solution 401. And I mentioned that one specifically because, in my opinion, it's a little bit conservative of a default convergence criteria there. So it defaults to a 0.1% criteria on your bolt preload. But generally speaking, bolt preloads, when you're torquing them down, you're going to have, 25% uncertainty in that preload based on torque. So it's a little strict, and it can cause the solver to iterate a lot unnecessarily, because it can tend to, I usually set it to like 1%, because it can iterate a little bit to get to 1% and then a lot more to get to that 0.1%, and 1% is usually good enough. And then lastly, we're going to talk just to cover a few 402 specific parameters. So for contact, there's the end side parameter, which I find myself using mostly because I'm kind of lazy. And it basically toggles on double-sidedness for shell contact. So that way you don't have to look at your shell normals to figure out which way they're contacting from. Kind of just a quick fix. But it specifically exists there because if you have a ribbon that is self-contacting on both sides, then you definitely need it to look for contact from both sides of that ribbon. There's also the p-depth parameter, which is basically your search distance parameter that you're defining in solution 402, which is in a slightly different spot than the 401, which is why I mention it here. In terms of solution control, the one that I find myself using a lot in 402 is the line search parameter, the INLS. And that's basically if I have a solution 402 that's behaving a little bit unstably or not converging well, line search is something I almost always am going to consider turning on. And then if you're giving it a positive value, it's using an energy method. If you're giving it a negative value, it's using a force method. And then the absolute value of that integer is how often it's active after how X number of iterations. And then the last parameter we're going to talk about is the IT max parameter in solution 402. I generally think 402 is a little bit conservative with the maximum number of iterations. It defaults to 10. I find myself bumping that up more often than not, which is why I mention it here. So now we're going to get into a quick little demo of, let's say you have a bracket that is showing some plasticity in it based on your linear analysis. So this particular bracket is 6061 aluminum, and I have a load on this point here. It's bending the bracket down, and it's creating some yielding in this area, especially when we consider our factor of safety. So there's a 36 KSI yield stress for aluminum 6061 with a 1.25 factor of safety. This is what your yield region would look like. Then if we take that model and say it has shown yield, we run it nonlinear, you see how that stress redistributes, and because it's a nonlinear analysis, it's up at 36 for the color bar limit there, but we'll talk about that as we get into it. So I'm going to switch over to an NX window here. So that should look very familiar. That's the yielding that you should have seen in that picture just before. So I'm going to return to the model here so you can kind of see the setup here. It's 4 bolts that are restrained at the bottom here, a bracket representing some component that's attached to this with a CG offset here, and I've just got a load at the CG of that, pushing that guy down, causing that bracket to rotate. So right now it's a 101 solution. So the first thing that we're going to do is we're going to create a new solution of the 401 type. If I scroll down, so 401 multi-step nonlinear. I'm going to call it a Sol 401 and create the solution. And because I know that I want plasticity in this solution, I'm going to come down to this bulk data tab here, and I'm going to, before I forget to do it, check the box to turn on my material nonlinearity. Because remember, if you don't check that box, even if you feed it stress strain data, it will not actually do a material nonlinear analysis. So I'll say OK to then create that solution, and now I'm creating a step. So I do just want a standard nonlinear static type stat. I don't want to do this as dynamics. So that's the defaults there are what I want. So I can create my step. I am going to go ahead and set the number of increments to 10. So that way I see the progress as the solution is going through the load, and I don't just see the end state. So I can see the load ramping up as it gets applied to the model. And I'm not going to set any control parameters as of yet, because my default with the new problem is I leave all of the defaults on. So I'm not going to change any of those nonlinear control parameters. So now I have my 401 solution created in here, but I don't have any loads on it yet, or constraints. So I'm going to copy or drag down my constraints into the solution. And then I'm going to create the loads container here. And one thing to keep in mind with a nonlinear solution is, if I go back to this guy, if you remember, I was looking at this with a nonlinear, I was doing a linear analysis with a factor of safety. So I was scaling my effective stress by dividing my allowable to get the correct loading with my factor of safety. Because I'm doing a nonlinear analysis here in NX, I actually have to scale my loads up by the safety factor, so that way when you are using the plasticity curve that you feed the model, the load goes all the way into that regime of plasticity. So I can't just take this existing load and copy it down. What I need to do is I need to copy my load, and I'm going to edit that load, and I'm going to multiply it by my 1.25 safety factor, and I'll call it nonlinear force. So now that I've scaled my load, I can apply that into my subcase, and now I have the load. So that's the solution setup, but I don't yet have material properties in here to do any of that material nonlinearity. So I'm going to switch back to the FEM here, and in the FEM, manage my material and edit this material. And then if this box wasn't checked, I would check this box up here to turn on the ability to see the area to put in your stress strain curve. Since it started checked for me, I can just use it there. But what I want to do is I want to create a stress strain curve. Since I'm not doing a bilinear, if it was bilinear, I could just put a single H value here. But since I'm applying a curve, I'm going to create a new field of the table type. And it's going to be with respect to strain that I'm creating that table. In terms of the table options, linear interpolation is totally fine, so I don't need to change anything there. And then for the stress strain table, I'm going to click this button to edit the table in an Excel spreadsheet, which will take just a second to load. That one on the other screen. So that pops up this spreadsheet. Because I knew that I was going to be doing this demo, I already have a spreadsheet with aluminum 6061 stress strain properties in it that I've defined. So I'm just going to copy my data out of that spreadsheet into this worksheet for the Nastran solution, or for the NX solution, I should say. And one thing to note, and an easy way to screw up here, is you see that the headers on these say millimeters per millimeter in MPa, whereas my values are in inches per inches PSI. The strains don't really matter because it's unitless, but that stress is incorrect. So even though the header is incorrect, what I'm going to do is close out of this so it goes back to NX and tell it to update. And you'll see it populate here in just a second. So now I have the table there, but the units are wrong. So then I can click on here and change the units for the variable to PSI. And I might as well change these to inches per inches just to be consistent, even though it doesn't really matter. So now I have my stress strain table for that material in the appropriate units. I can say OK to that. And I have now added my nonlinear material to my FEM. If I go back to the simulation, that material is in the underlying FEM, and all I have to do now is right-click and tell the solution to solve. I'm not going to make you guys sit around for however many minutes it takes for this solution to solve. So what I do have is one where I already ran it. Let me get that out of the way. I already ran the solution. So you are now looking at the results that would end up when that solution finishes. So you see those 10 increments of the solution. So you can see the load ramp up over time. You'll note that I did set my color bar limit to the 36 KSI yield stress because I already applied the factor of safety in the load. I don't need to factor, and I shouldn't factor my allowable because it's a nonlinear solution. You're in the yield region of the curve. So you're behaving nonlinearity, so you can't just scale your results anymore. But if I want to, I can also go back through the increments and see how the load progressed into that nonlinear realm. If I go back to a 1-to-1 absolute, you can see this bracket bending over time, and that yield front forming in that solution. Likewise, if you wanted to analyze for the ultimate strength case, you could do another solution with another load where you would create a separate solution. You would change your load scale yet again to, assuming you had like a 1.5 factor of safety at ultimate, you would scale your load up to the ultimate, and then you'd be comparing to, I believe it was a 42 KSI ultimate strength in your solution. So that covers the demo. Now I will open it up to the Q&A.
Very good. Thank you very much, Miles. So Jonathan and I will handle the Q&A, and we'll let you handle the answers.
Sure.
The first question we had was, and we believe you've already answered it, is what is meant by large strains? And your presentation showed 0.3%, or was it 3%?
3%. Yeah. So it's a little shaky because it's not exactly 3%, but generally speaking, large strains are necessary because the default element type is a small strain formulation, which by its nature, that small strain formulation breaks down with internal element energies once you get above around 3% strain. And that's why you need to switch over to a large strain type formulation. So it's not exactly 3%. That's just kind of the rule of thumb where you start seeing that happen. But if you only have a couple of elements in your model that are at large strains, you can probably get away with like 8 or 10. If you have a lot of your model, it might be 2.5 or something. I don't know.
Okay, so there was another question which I'll answer right away regarding the recording. I did mention at the beginning, but some people were not with us at the very start. Yes, today's session is being recorded, and it usually takes about a day or so for the recording to be posted. And everyone who registered for the webinar will receive an email with a link to the recording. So no fear there. If you want to come back and review it again later, or make it available to colleagues or friends who are interested in this topic, that will be available too. So the next question here, Miles, is can you update autoscal, the autoscal parameter in subsequent subcases so you can get a soft contact stiffness in the first subcase and then increase the contact stiffness in subsequent subcases to decrease penetration?
You can absolutely do that. What you're going to end up doing is you're going to change your contact definition from one subcase to the next. And so for solution 401, contact can be changed subcase to subcase, and that contact change is a step type behavior. So it would behave exactly as you want, because you're basically taking away an existing contact and replacing it with almost an exact same copy with just a slight different stiffness parameter to it. So that should behave pretty much like you would expect it if you are only tweaking that one parameter. I mentioned that 401 behaves that way because 402 ramps contacts on and off by default. So if you are doing the equivalent in 402 where you're changing your stiffness from one subcase to the next, you probably want to put a preload subcase in between, so that way the ramping happens in that little preload subcase, and then you proceed with the next nonlinear static type subcase, for example.
Sounds good. And if that didn't answer your question fully, Ryan, please ask a follow-up if you wish. And from Joshua, ELAR sets are only compatible with 401 and not 402, correct? Are there plans to add the capability to 402?
I'm not familiar. ELAR sets? That I'm not quite sure on that one.
So Joshua, I'll ask you to clarify in your question, and Miles will get back to you. We also have a question: does Femap support 401 and 402 multi-step nonlinear as well as Simcenter 3D?
Sorry, can you repeat the question?
Does Femap, as well as Simcenter 3D, does Femap also support solution 401 and 402?
Oh, yes, it does. Absolutely. There's a slight lag in the Femap support with respect to the new developments that are released in solutions 401 and 402. So it's not always that they have the latest and greatest tweaks. It sometimes takes them one extra version to implement the necessary checkboxes for all of the newest features. But they do, at this time, with the newest versions of Femap, support the vast majority of all functionality in solution 401 and 402.
Terrific. So Joshua has clarified his question. He says ELAR stands for element addition and removal sets, and it replaced EBD set in solution 601.
Oh, yes, I remember now. So apologies. Yes, so to my knowledge, 402 does not have element birth and death capability at all. And for 401, it's rather new and limited is my understanding. I haven't spent a lot of time dealing with that though.
If that was a need that you felt you had, perhaps for some historical reason, how would you work around the fact that the 401 or 402 don't have it fully?
That is a complex question. I mean, the answer would, if I absolutely needed element death, what I probably would be doing is going to a different solver, to be completely honest. I know they're adding that capability, so it could also be that that answer changes in a few years' time. But at this time, it's not as good in my understanding as it could be or was in 601, for example.
Sure. And, as most of the people on this call are aware, both Femap and Simcenter 3D can use a multiplicity of solvers. Nastran is naturally our default solver here at ATA, but we routinely use others, Abacus. I'm not sure about LS-DYNA, but the right tool for the right job. And the preprocessor in Simcenter 3D and in the preprocessor in Femap can support multiple solvers if needed. Okay, do we have any more questions for Miles before we wrap up today's session?
Yeah, I will jump in and catch another question that just came into the chat. And that was a question, kind of just like a Siemens terminology question. We were saying Simcenter 3D, but if you're paying attention closely, you saw that Miles had an application open that at the top said NX. And so just wondering, NX versus Simcenter 3D, are they the same? Are they different? Back in the day, right, this was all just a single NX. And at the time, we said NX CAE was part of NX. And so you would start NX and you could do all your simulation. A couple of years, maybe 5 years ago now, maybe longer than that, they split the simulation capability out into its own product. And so that's Simcenter 3D. That's its own standalone application that you can, launch, you can license and then start Simcenter 3D. You can pull in CAD from any source and then go forth and do your simulation. But Simcenter 3D still has NX at its core, to the point that the full Simcenter 3D capabilities are actually part of NX. So in this case, yes, Miles did start NX, imported CAD and was doing his simulation in NX. He also could have done that entirely within Simcenter 3D. So in this case, my understanding is everything in Simcenter 3D is also part of NX. I don't think the inverse is true, right? So it wouldn't make sense that all of NX CAD and all of NX CAM would be in Simcenter 3D, although Simcenter 3D does have, geometry cleanup and so some CAD functionality like that within Simcenter 3D.
But you're not going to be doing drafting in Simcenter 3D, for example.
Right. Yep.
So before we totally wrap up, I do want to give you an opportunity if you are interested in these solutions and don't already have access to them, either because you haven't purchased the Simcenter 3D or Femap option for Nastran Multistep Nonlinear, or you don't have the tokens. There are Simcenter 3D tokens that also enable this capability. If you are interested in obtaining access to Multistep Nonlinear, let me know and we'll be happy to help you out. Thank you for joining us today for today's webinar on getting started with Nastran Multistep Nonlinear Solutions, one of our ATA educational webinar series. Thank you for joining us, and please keep us in mind for the next webinar. We do try to keep you informed of them coming up, and thank you very much for joining us.